In this video, we're going to take a look at electric potential, really just the conceptual understanding of it. We'll look a little bit more about the mathematics in the next one. But the idea of voltage and potential, and see how our understanding of gravitation and energy allows us to think about this. We're going to start with this. This is a topographic map. Where is this? I don't know if you can tell. Belfry Hill Monument. So that's right, here in Lexington, not that far from the high school. It's a hill. Right? And so if we were to think about this hill, we might start by thinking, where would the gravitational potential energy be maximum? Well, if we look carefully here, we can see that there is a point labeled as 267.1, which I think is feet above sea level. And that is going to be our highest point here on this map. You could then ask the question, where is UG a minimum? You could look around and it turns out it's somewhere down around here in the 2-teens. 218 to something, somewhere down in that area. Okay. There's the satellite view of it, right? Little hill near the library. So if we think about what's happening here, at the top of the hill, you have more gravitational potential energy if you're there, of course. But we could also break it down by saying, how much gravitational potential energy do you have per kilogram? Meaning that in some ways, this is a more useful metric because it tells you how much gravitational potential energy any kilogram of mass would have there. And that would be a way of saying, okay, well, I could put any object there and I could just figure out how much potential energy we would have by knowing this one quantity. And so we call that place a place with high gravitational potential. The base of the hill, the lowest point, has what we call low gravitational potential. It is true that an object in either of those places would have high and low gravitational potential energy, and that's what we mean by this thing. In some ways, it's very much like the electric or gravitational field, right? There are places with field strength, and then if you place something there, it experiences a force. In this way, if you have something with high gravitational potential, if you place a mass there, it will have high gravitational potential energy. And then the last sort of definition here is there is a potential difference between these 2 points because there's some potential at the red dot and some potential at the blue dot. So what about these contour lines? What do they tell us? Well, if you think about walking along one of those lines, what would happen? Well, you would be at a constant gravitational potential energy or a constant gravitational potential because it's all at the same height above sea level. Right? So these contour lines are what we call equipotential lines or lines of equal potential. Your potential is the same everywhere on that line. So we can do another thing. If you imagine sort of traveling down along this, what is the line of net force? Well, we know we're not going to sink into the hill. We're going to be pulled along it because there's a normal force and a force of gravity. And so if you could kind of imagine what net gravitational force or force you would experience on this if it were a slippery hill sliding down, right, we can call these the field lines. These are sort of the gravitational field lines or related to it. And it turns out that they're always perpendicular to the lines of equipotential. And that is because if you were to sort of let something move down it, this would be the steepest way of traveling down that particular path. So the net force is going to be the greatest where the contour lines are close, right? We remember this, hopefully back from our energy unit, that negative du dx, the rate of change of the potential energy as a function of distance, the negative of that gives you the force. So where we have the steepest slope, change in potential energy with respect to distance traveled, we get the biggest force. So we can think about this in terms of what happens. Well, if you were to release a marble from the top of the monument, it would roll along that path down to the bottom of the monument, to the lowest point, and it would go in the direction from high to low potential through a potential difference. On flat ground, the ball's not going to roll. Right? So if there is no potential difference, no height difference in this case, then it wouldn't roll. So this leads us to thinking about electric potential energy versus electric potential. Now, we know that there's high gravitational potential energy when you lift something up in the air and low when you leave it down, high potential, low potential, right? That's the way this is defined. So the electric potential energy is the energy of an actual charged particle in that position, whereas the potential is a property of a point in space. And so the relationship between potential and potential energy is potential energy divided by the test charge. This should look a little bit familiar because this is also how we define field in relationship to force. We divided out the test charge and said, well, this is the property of that point in space, right? So we can think about field and potentials by looking at a monopole, a single charged particle, say a positive Q. We already know that the electric field line should be radially outward, right, getting weaker by 1 over r squared as it goes. So electric potential can be thought of as bringing in a positive test charge, seeing what the electric potential is, potential energy is, and then dividing out the Q naught. And so we can figure out in these concentric circles, they're actually spherical shells. Around this, we have what we call equipotential surfaces, places where the potential energy for a given charge would be the same. Highest potential is close to Q, low potential far from Q, right? From the positive Q, because that bringing in a positive test charge, you're going to have to do more and more work to bring it in, storing more and more potential energy. The difference between the potential at A and B is what we call a potential difference, also known as a voltage. And this is what your voltmeter, your multimeter, has been measuring, a difference in potential energy per coulomb of charge, right, between 2 points in a circuit. So when we talk about voltage, we're talking about the electric potential difference between 2 points. So the vocabulary can be a little confusing. We've got 3 terms that all sound a little bit the same. We've got electric potential energy. We've got electric potential, which is the electric potential energy per charge at a point in space. And then we have electric potential difference, which is the difference between the electric potential between 2 points in space, which is also sometimes called voltage. Interesting. You'll notice that electric potential and potential difference are both measured in joules per coulomb, which can also add confusion because that's called a volt. That's the unit. Voltage is measured in volts, so is potential. Potential gets the symbol V, voltage delta V, although sometimes we just write it as V. So positive charges want, quote unquote, to move from high to low electric potential. They would be pushed. That's the way the electric field goes. It's kind of like being up on a hill. The object naturally wants to roll down the hill. So we're going to use this sort of analogy between gravitation and electricity to help us visualize what's happening here. So this is a dipole. We've drawn the electric field lines of this before in a previous unit. What do the equipotential lines look like? Well, they look something like this, right? We've got these electric field lines, which are in sort of pink here, and then we have the equipotential lines in purple. You'll notice where they cross, they're always crossing perpendicular. This is sort of a three-dimensional picture of what we might want to call this, where the electric potential strength and magnitude is represented by the height, the z-axis, whereas the xy plane represents, the physical space. It can be helpful, but if you're moving along in one dimension, you would say, oh, it's like really high up in the air when we're close to the positive, high positive potential. And when you're near the negative charge, you have really, really low potential. This one uses red and green. Often you see red and blue. I think that's probably more common as to what you see. So for the dipole, electric potential is positive near the positive charge, and it's negative near the negative charge. Where is it zero? Well, there's kind of two places that we think of it as being at zero. We think of it as being zero right in the middle, right? Where we've got this kind of, saddle. You're going from negative potential to positive potential. So of course you have to pass through zero, and there's a line where that would be true. And then also when you're infinitely far away, right? When you're infinitely far away in any direction, you also have zero potential. We can also think of this in terms of something like a battery or a separation of charge. Well, what does a battery do? It's actually trying to push charge from the negative to the positive, the opposite direction that it wants to go. It wants to maintain a potential difference, which allows things to go around the circuit. And that's something that it does via a chemical reaction, right? So let's talk a little bit more about this gravitational landscape examples. This is in your packet, and you can follow along with this one. But if you have a test charge, has more electric potential energy close to positive Q, we release positive Q. A mass has more gravitational potential energy at the top of the hill, release the mass. And so what happens? The test charge gets pushed away from A to B. We have a potential difference. The mass rolls down the hill from A to B, a potential difference in gravitation. What about something like this? This is a classic example. Why doesn't a bird get killed when it lands on an uninsulated high voltage, high potential wire? Well, the reason why is both of its feet are at the same potential. It's a high voltage wire. The potential is high here. But it's just like there's no difference in potential energy between 2 points on the top of a hill. There's no difference in potential energy per charge between those 2 points on that wire. Ball doesn't roll from A to B, therefore no charge is going to be pushed around in there. All right. Now, what about between C? Well, there is a potential difference between A, B, and C. So we can also do this with oppositely charged plates. This is essentially a capacitor, and we're going to learn about those. If you have a bunch of positive charge and a bunch of negative charge, we start by drawing the electric field lines. We've already learned between two parallel plates, we get this uniform electric field. At the edges, there's some edge effects, but we'll ignore those. And the electric equipotential lines. Well, it's easy. If we have a bunch of parallel lines, then the equipotential lines should all be parallel to each other and perpendicular to those. And because they're nice and even, a uniform field, we have nice even lines of equipotential. And so you could ask yourself, at which of these points is V positive, the potential positive? Well, if there's negative charge and positive charge, we expect there to be sort of zero potential along the middle. So if you're closer to the positive charge, A and B would have positive potential, like being uphill. And for C, it would be negative potential because you're closer to the negative side of the parallel plates. Which points have a voltage between them? Either A and C or B and C. A and B are along the same line of equipotential, even though I didn't draw one there. There is one there, right? They are the same distance across the plates. We could look at a positively charged sphere, right, and think about the potential and the electric field now. There's some examples of this kind of stuff. If you are at point A, then the electric field is going to be pointing radially to the left, outward, right? And the potential will be positive because you are near a positively charged object, which is like being up a hill, up the slope. If you are at point B, there will still be a positive potential because potential is only zero, infinitely far away, or halfway between positive and negative, well, somewhere between positive and negative charge. And the electric field will be zero because you are inside the sphere. So what is this like? Well, B is like at the top of a plateau on a hill. A is like being on the slope of that hill. If it's a negatively charged object, well, at point A, the electric field should be pointing toward the negative charge because that's what a positive test charge would experience. And V, the potential, should be negative because it is near a valley, a negatively charged object. At point B, we have a negative potential and zero electric field because you're inside a spherical shell, or inside of a non-conducting spherical shell. So the electric field has to be zero. For C, it's negative potential again, but this time the electric field is to the left, always pointing toward the negative charge. So what is this like? This is sort of like being at the bottom or having a hill, or not a hill, a valley or a hole dug, where A and C are different distances up out of the hill. Neither of them are up to zero, and B is down at the bottom of it. So that's the conceptual overview of the electric relationship between electric field, electric potential, and electric potential difference, and talking about how it kind of relates to gravitation.